Welcome back to the deep dive. All right, today we are taking a hard left turn.
Yeah.
We've spent a lot of time on AI that feels, intuitive neural nets, reflex agents, but today we're stepping into the cold, hard world of logic.
It's a very distinct shift. I mean, think about it. The agents we've talked about before are basically pattern matchers.
Right, they see something, they react.
Exactly. It sees a wall, it turns left. It's effective, sure, but it's shallow. Today we're talking about agents that actually know things.
We're moving from instinct to intellect, knowledge-based agents. So these machines don't just react, they build a model of their world. They reason.
They can figure things out they've never seen just by, just by thinking about it.
Yeah.
And the core of that, the brain of the operation, is the knowledge base, the KB.
A knowledge base? That sounds like a corporate wiki or something.
Yeah, it's a bit more fundamental than that. Think of it as the agent's entire worldview, all stored as a set of sentences in a formal logic language.
And it only interacts with this brain in two ways.
Just two. Talia and askare.
Simple words. What do they mean here?
So, tell is the input. The agent's sensors pick something up, maybe a smell, and it tells the knowledge base, there's a smell here. It adds a new fact.
And ask is how it makes a decision.
Precisely. It asks the knowledge base, okay, given everything I know, what's the safe move? And the magic is, it doesn't just look up an answer. It derives it using logic.
That's a huge difference. It's like memorizing a guidebook versus actually understanding the geography of a city.
That's a perfect analogy. And this gets to a really key idea from the source material, the knowledge level versus the implementation level.
I like this. It's separating the what from the how.
Exactly. At the knowledge level, we just care what the agent knows. I know there's a pit in that square. It doesn't matter if that's stored as a linked list or, a bunch of firing neurons. That's the implementation.
Which is good because we're about to throw this poor agent into a scenario that sounds like an old text adventure game.
Oh, it really does. We call it the Wumpus World.
The Wumpus World. Okay, let's set the scene.
So imagine a dark cave. It's a 4x4 grid of rooms, and you, the agent, start in the corner, square 11-1. Your goal is to find a pile of gold and get out.
But it's not that simple, of course.
Of course not. Somewhere in there is the Wumpus, a beast that eats you if you enter its room. And there are also bottomless pits. You fall in, you die.
And the agent can't see any of this. It has no map. It has to figure out the world based on its immediate surroundings.
Right, it relies on these little clues. If you're standing in a square right next to the Wumpus, you smell a stench. If you're next to a pit, you feel a breeze. If you're in the same square as the gold, you see a glitter. And if you walk into a wall, you feel a bump.
And you have one weapon, an arrow.
One single arrow. You can shoot it, and if it hits the Wumpus screams and dies. You hear that scream from anywhere. But you only get one shot.
So stench, breeze, glitter, bump, scream, that is the agent's entire reality. It has to survive on that.
It's a test of pure deduction. A reflex agent might just say, if stench, run away, but that doesn't work. You have to use logic to pinpoint the danger.
Let's actually walk through a game. I want to feel the gears turning here.
Let's do it. So you start at 11-1. The rules say that square is always safe.
Okay, so we check our sensors. No stench, no breeze.
And that's our first big inference. Because there's no breeze, the agent knows for a fact that the squares next to it, 1 and 2 and 2-1, can't have pits.
And no stench means no Wumpus.
Yeah.
So we have two safe squares. Okay, let's move east to 2-1.
You step into 2-1, and your sensors go off. You feel a breeze.
Okay, panic time. A breeze means a pit is right next door.
Right. And the neighbors of where you are now are 11-1 behind you, and two new squares, 2-2 and 3-1.
Well, we know it's not 11. We just came from there. So the pit has to be in 2-1 or 8.
Or 3-1. But, and this is the key, the agent doesn't know which one. A dumb agent might guess.
Right.
A logical agent knows what it doesn't know.
So it retreats.
Exactly. It goes back to 11-1
Yeah.
and tries that other safe path we found earlier.
Yeah.
North to 12-2.
We're in 12-2. We check sensors. No breeze here. But we smell a stench.
Okay, a lot just happened. First, the breeze. There's no breeze in 12-2. What does that tell us?
Well, its neighbors must be safe from pits. So that's 1-1, 1-3, and wait, 2-2.
Yes.
2-2 is a neighbor. If there was a pit in 2-2, we'd feel a breeze right now. But we don't. So 2-2 is safe.
Which solves the mystery from before. We knew the pit was in either 2L2 or 3-1, since we just proved it's not in 2Bell.
It must be in 301. Wow, we found the pit without ever going near it.
That's logic. Now, for that stench we smelled in 12-2, the Wumpus is nearby. Neighbors are 11-1, 1-3, or 2-2.
Not a 1-1, that's the start. Could it be 202?
Think back. When we were at 2L1, did we smell a stench?
No, just a breeze. No stint.
Exactly. So if the Wumpus were in 202, we would have smelled it from 201, but we didn't.
So by elimination, it's not a level 1, it's not 202. The Wumpus is in 133, definitely.
Bingo. We've located an invisible monster in a bottomless pit just by combining two different experiences over time.
That is so satisfying. But to make a computer do this, we can't just talk it through. We need a formal language. This is where syntax and semantics come in.
Right. We use propositional logic.
The logic of facts.
Yep. The syntax is just the grammar. We use symbols like doors for pit and doors for Wumpus, and we connect them with A and D or not, and the really important one implies...
That implies arrow is doing a lot of work. Pit at 2N2 implies breeze at 2N1.
That's the syntax. But the semantics is where it gets a little trippy. Semantics is about truth in what we call possible worlds.
Wait, possible worlds? That sounds like we're discussing the multiverse.
In a way, we are. A possible world is just one way the cave could be laid out. In one world, the Wumpus is here. In another, it's over there.
And the agent's job is to figure out which world is the real one.
Or at least what's true in all the worlds that are still possible. This is the idea of entailment.
The double turnstile symbol.
Yeah. We say the knowledge base entails a sentence if that sentence is true in every single possible world where the KD is true.
The source used a great analogy for this. The haystack.
It's a classic. The haystack is all the logical consequences of what you know. The needle is the specific thing you want to ask, like, is the Wumpus in 1 and 43? Inference is finding that needle.
And one way to do that is just to check every single possible world, one by one. Model checking.
You can do that. It's guaranteed to be correct. But there's a huge problem.
Math.
Specifically, an exponential explosion. If you have a squares, you have 200 impossible worlds. For our little 4x4 cave, maybe that's fine. But for a real problem with 100 variables.
You'd be calculating for hours.
Oh yeah, $200 is not a number you want to deal with. So brute force is out. We need a shortcut.
We need to prove things without checking every universe.
And that brings us to theorem proving. We apply inference rules to derive new sentences from old ones.
The most famous one being modus ponens.
Latin for the mode that affirms. Super simple. If you know A implies B and you know A is true, then you know B must be true.
If rain implies wet grass and it is raining, then the grass is wet.
Exactly. But for computers, there's a more powerful all-purpose rule called resolution.
Resolution. Okay, this one sounds like a diplomatic treaty, but you said it acts like a garbage disposal.
That is actually a great way to put it. It takes two clauses that conflict and smashes them together. Say, either the butler did it or the maid did it.
Butler or maid. Got it.
And then you learn a new fact. The butler did not do it.
Well, then it has to be the maid. Right.
That's it. That's resolution. The butler and not butler cancel each other out. They get disposed of, and you're left with the maid. And it turns out, if you convert everything into a standard format.
Conjunctive normal form. Big string of ORs connected by A and Ds.
Right. If you do that, you can use that one resolution rule to prove anything that's provable. It's complete.
But is it fast? We're still trying to beat that explosion?
It's faster than checking every world, but inference in general is still hard. So we can cheat. We can restrict the language to something simpler, like horn clauses. Then things get incredibly fast.
Horn clauses. What makes them so special?
A horn clause has, at most, one positive thing in it. They basically look like, if A and B and C are true, then D is true.
That feels very natural. If I have flour and sugar and eggs, I can make a cake.
Exactly. It's a causal chain. And because of that simple structure, we can use linear time algorithms. The time it takes grows in a straight line with the data, not exponentially.
That's the holy grail of efficiency.
And this leads to two really intuitive strategies, forward chaining and backward chaining.
Forward chaining is data-driven. You find a clue and ask, what does this mean?
Yep. You see the glitter, you infer gold, you infer grab it, you ripple forward from facts.
And backward chaining is goal-driven, the where are my keys method.
Exactly. You start with the question, is the Wumpus in 183? And you work backward, trying to find a rule that proves it, then trying to find the facts that support that rule.
Okay, so we have the tools. But let's get to the industrial scale. Real problems have millions of variables. This is where we need the modern solvers.
This is where we get to algorithms like DPLL.
Davis, Putnam, Lodgman, and Loveland. What makes DPLL the heavyweight champion?
It's basically a very, very smart backtracking search. It explores the tree of possibilities, but it uses these clever shortcuts, these heuristics, to prune off huge branches of the tree before it even explores them.
What's an example of a shortcut?
My favorite is the unit clause heuristic. Imagine you have a really complex logic puzzle, but one of the clues is just A has to be true.
Well, okay, then A is true. You don't have to guess.
Right, but here's the magic. Once you lock in A as true, that might force B to be false. And that might force C to be true. It creates this cascade called unit propagation.
Oh, it's like Sudoku. You find that one number, and suddenly you can write in 10 others immediately.
Exactly like that. But sometimes, even DPLL is too slow. Sometimes you just need to guess. And that's WalkSAT.
WalkSAT feels chaotic. It's a local search algorithm.
It is. It doesn't prove anything systematically. It starts by just assigning random true or false values to everything. It's a complete mess.
Full of contradictions.
Massive amounts. And then it just looks for a conflict and flips a variable from true to false or false to true just to see if it helps.
So it's like trying to solve a Rubik's Cube by just randomly twisting the parts that look wrong.
Pretty much. It's a mix of greediness, fixing obvious errors, and randomness. Just flipping things to get out of a jam.
Why the randomness? That seems so counterintuitive for logic.
To escape traps. Sometimes you get stuck in a state where any logical move makes things worse, but you still haven't solved the puzzle. A random jump can kick you out of that rut.
The big catch with WalkSAT, though, is it can't prove something is impossible.
Right. If it runs for an hour and finds nothing, you don't know if there's no solution, or if you just got unlucky. It's fast, but it's incomplete.
Now, in studying these, researchers found something bizarre about logic problems themselves. The phase transition.
This is one of the coolest things in AI theory. You'd think that harder problems are just bigger problems, but it's not true.
It depends on how constrained they are, right?
Exactly. Imagine a graph. On one side, you have problems with very few rules. They're easy to solve because there are a million right answers. Under-constrained.
Find a number greater than 0. Easy.
On the other side, you have problems with tons of rules. Those are also easy because you hit a contradiction almost immediately, over-constrained.
Find a number greater than 10 and less than 2. Also easy because it's impossible.
But right in the middle, there is this cliff, a very specific ratio of rules to variables. For a standard problem type, 3SAT, it's about 4.3.
4.3.
At that exact ratio, the problems become exponentially hard. They're on the knife edge of solvable. That is where the computer sweats. It's where the universe of logic fights back.
That is wild. Okay, so we've solved the logic, but we've ignored one huge thing this whole time. Time.
Ah, yes. The agent moves. The world changes.
And this leads to a famous headache in AI called the frame problem.
It sounds technical, but it's a deep problem. Logic is great at saying what changes. I move forward, now my location is different. Easy.
But it's terrible at saying what doesn't change.
Exactly. If I move from one square to the next, does the Wumpus move? Does the color of the walls change? Do my socks disappear?
Common sense says no, obviously not. But logic doesn't have common sense.
Right. If you don't explicitly write a rule that says moving doesn't change the wall color, the logic engine assumes the wall color is now undefined. You'd have to write millions of rules just to say nothing happened.
I moved and gravity still works. That sounds like a nightmare.
That's the frame problem.
So how do we solve it without writing infinite code?
With a clever linguistic trick called a successor-state axiom. Instead of listing all the things an action doesn't do, you make a rule for the property itself.
How does that work?
You say, this fact is true at the next moment in time, if and only, if an action just made it true, or it was already true and no action undid it.
So I am holding the gold is true if I just grabbed the gold, or I was already holding it and didn't drop it.
Exactly. It elegantly handles everything that stays the same by default.
And once you can handle time, you can finally do planning. This is SATPLAN.
Yes. You take the start state, the end goal, all the rules of the world, and you mash them into one gigantic logical sentence. Then you just throw it at a solver, like DPLL.
And you ask the solver, can this sentence ever be true?
And if it says yes, it spits out a solution. And that solution is the plan. It's a sequence of actions to get from the start to the goal.
But I heard SATPLAN can be a bit of a rules lawyer.
Oh, it's the ultimate rules lawyer. If you don't explicitly tell it you cannot do two things at once, it will invent a plan where you move and shoot at the same time to save a step.
Or shoot without having an arrow.
Exactly.
Yeah.
You need these extra rules, these precondition axioms and exclusion axioms. It just shows the AI is only as smart as the world you build for it.
So zooming out, we've gone from a simple reflex to an agent that reasons about invisible monsters, plans for the future, and navigates these crazy probability cliffs.
And the really cool thing is, this isn't just about hunting wumpuses. These solvers, DPLL, WalkSAT, they are the workhorses of modern industry.
Where do we actually see them?
Hardware verification is a huge one. When a company designs a new computer chip with billions of transistors, they can't just hope it works. They convert the circuit design into a massive logic formula and use these solvers to prove that it won't crash.
So the same math that finds the pit in the cave is making sure my laptop doesn't blue screen.
That's it. It's all just searching for truth in a haystack of variables.
I want to leave our listeners with one last thought. We've been talking about propositional logic this whole time, but did you notice how repetitive it is? We had to write a rule for breeze at 11:1, and another for breeze at 12:2, and another for breeze at 1 bail 3.
It's incredibly verbose. We had no way to just say, for any square, if it has a pit, then any adjacent square has a breeze. We had to list every single instance.
It feels like we're missing the ability to generalize, to say for all x.
And that is the doorway to first-order logic. But that is a deep dive for another day.
Indeed it is. Thanks for diving in with us. Keep your inference engines running and watch out for pits.